Okay, so welcome everybody to the Manchester Java community this evening or this afternoon, wherever you are in the world. Yeah, thanks for joining us. To start, I'd just like to say a couple of thank yous to our sponsors. Also, first of all, thank you to RecWorks, who sponsor our meetup fees. Really appreciate that. And thank you for the support we get from the London Java community as well. So this evening, we've got a very special guest that we're very excited about, in Monica. So welcome, Monica.
Thank you.
So I'm not going to introduce you in too much detail because you can do that better than I can, that's for sure. But Monica's a Java champion. She's an expert in the area of GC on the JVM. Spent a lot of time working with JIT GC and more recently ZGC or ZGC if you're in the UK. But yeah, I'll hand over to you, Monica. Thank you.
Oh, thanks. Thank you for reaching out, and thank you for having me here today. I'm glad that I could do it, and because if you're reaching out and talking about ZGC, I got a chance to play with it a little bit more, because the last time I did anything with ZGC was in an I think JDK 16, because I was trying to figure out the improvements that they had done with respect to the concurrent stack processing. So the entire evolution of ZGC was pretty interesting to watch, because that brought about lots of changes into the OpenJDK garbage collector. So I will not only talk about ZGC and the design considerations with respect to ZGC, but also talk about how it brought about changes that can be useful for other garbage collectors in OpenJDK. A little bit about myself. I work at Microsoft, and my field is basically any JVM or Java level optimizations that we can bring to Azure and other first-party customers within Microsoft. One of the biggest thing that we want to do is not only make these changes happen, but also bring this to the OpenJDK community, because we work very tightly with Azure services and other, like I said, first-party users like LinkedIn, Minecraft. So any kind of learnings we get from our partnership, we will bring it to OpenJDK and of course share the real-world experience there. So I'm really happy being where I'm today and being able to do that kind of work with Microsoft. So, and as you mentioned, Nick, my background is G1 GC mostly, doing the performance work for that. While doing the performance work, I learned a lot about the niche spots for G1 GC. So as you will see in the performance experiments that I've done with respect to ZGC, I've kind of stressed G1 to where I'm trying to break G1. And by breaking G1, I'm also trying to put the same pressure on ZGC and how these two garbage collectors react the way they're designed. And it's very interesting to me. And I'm really looking forward to using or recommending ZGC for certain cases and G1 for others. So with that, I think let's get started. Here's a brief agenda. One of the things that I thought would be interesting is kind of show how these garbage collectors evolved, right? Especially within the OpenJDK space. And then from there, go and talk about ZGC and its nuances, like, certain things that are very ZGC specific. And then eventually compare ZGC with G1 GC. And I'm not trying to bring one GC down, because G1 is my baby, and it's, I'm still very impressed with the improvements it has undergone. And I'm also very impressed, and I think still, having it as the default collector is the right decision. So ZGC is now showing that it's very powerful with respect to low latency applications, and that's where its market lies. But G1 is the current default, and I'm all for it. Okay. So nothing negative about G1 here with respect to the comparisons, but I have to do these comparisons to highlight how ZGC is the app choice there. So let's design an adaptive, predictable GC, okay? So before we jump into the design, I wanted to talk about certain things that OpenJDK collectors have decided from the very beginning. The collectors were designed with different optimizations in mind because they were trying to target different goals. So there is the throughput collector, parallel GC. There is this client collector, serial GC. There used to be something called CMS, which was mostly, concurrent marking and sweeping. It didn't have compaction, so that compacting collector was added later on, and that was the fallback collector. Then we also moved to G1, which was kind of like between, being latency sensitive and also sensitive to throughput. So it's kind of playing in between the latency GCs and the throughput GC. Yeah. And one theme between all these collectors is that they were generational, right? So that was a design choice made by OpenJDK to have these kind of generational collectors, because the whole concept of generational collector is that it's based on the principle that most objects die young. So when these objects die young, you can do sort of these inexpensive pauses to collect these, and while collecting these dead objects, you're also aging the live ones. So as you age them, you say, okay, now you have passed this aging threshold. So that means you are longer term live objects, and eventually they could form your live data set. So and then if you try to move these live data sets back and forth, then it becomes very expensive. So that's the concept of generational. So you move them you kind of promote them to the old generation, and then you don't touch them. You just compact any kind of noise, or let's call it transients. So you just compact and collect the transients, and these guys stay, the live data set stays in the old gen. And this helped OpenJDK right from the get-go. If you compare it with any other runtime, it has kind of one of the best collectors for the purpose. And this generational concept helped with scaling and then maximizing throughput. The other thing that you would see with OpenJDK is that it uses parallel threads, right? And the concept of distributing the work, it's not a new concept, right? You apply that in networking theories and all those things. So the point is that you have this work queue, and you want to get to the end of the work queue. There could be a single thread going off and doing the work, coming back for the next job segment, and then the next job segment, and so on and so forth. But this GC work needs to be done every GC cycle. So if we employ multiple threads to help out, so you apply the queuing theory to this, so basically termination protocol and work stealing and everything. And then you have this really sophisticated collector. So that helped out. So these two are the principles that OpenJDK collectors are based on. So if today you don't know of an OpenJDK collector that's generational, rest assured that it's going to come in the future. And that's what CGC has just recently announced. They announced their generational collector, because that's the principle of these collectors. Okay. So with that in mind, let's design a garbage collector. So I talked about the generational part of it, right? And when we talk about generational, you have the young and the old generation. That's like a staple in OpenJDK world. There are other runtimes may have other generations. Sometimes the generations are based on the size as well, and they have their own collection and stuff like that. But you can think of OpenJDK collectors as always being a young generation and an old generation, because that seemed to work for us really well. Now, when you have generation, there is an overhead, And then the overhead is because we're dealing with references. So when we say these collections, and these collections are independent of each other, and as we move live objects or promote live objects, right, or move them within the old gen, we need to have track these references. And so to be able to do these like old to old or old to young references, there's a tracking overhead. So, you can call it as like the card table maintenance barriers. And every collector has their own overhead with respect to that as soon as you add the generational part to the collection, right? The other part, like I said, having multiple threads do the work, right? The easiest of them is to employ them in a stop the world fashion. So you have multiple GC threads and you stop the application thread and you tell it like, just wait for me to get the GC work done. I promise I'll do it really fast. So the application threads have stopped and the GC is doing its work. The GC gets done with its work and gives the control back to the application threads. So that's the easiest one. Sometimes that is not helpful, especially if you're trying to say that, hey, I have a pause time constraint here. So even if you go away and do the work, I still need the work to be done in less than 10 milliseconds. So I want that guarantee. So at that time, what you do is like, okay, I promise I won't take more than 10 milliseconds. And if I see that I need to, then I'll break up the work further. So we'll do it in incremental phases. And many of those incremental phases can happen along with your application. So that's called concurrent work. So the GC work can happen concurrently as well. But when you're working along with your application threads, there is something called maintenance barriers, because now the application thread can be mutating the live object graph at the same time as you're trying to keep a track of live objects. So you don't want, first of all, you don't want your GC to ever lie, right? You want it to give you the exact count of live objects. But the worst case would be if the application added another live object to the thing, but you never accounted for it in counting. So that's the worst case, because now you just lost track of a reference that was live. So what happens is that you have these maintenance barriers, and also you have a conservative approach that these GCs say. So they'll say implicit lives, anything. So they have these algorithms that go implicit live because they haven't yet marked it. So these kind of concurrent collectors have their own overhead in terms of heap occupancy, where they may keep something called floating garbage around, right? So floating garbage is that there's no live object in that space, but we haven't marked it yet. We haven't reached to accounting for all the live objects yet because we're doing it incrementally. So let's assume that they're all live. And so that's the overhead that you will find in all concurrent collectors. And of course, there are some barriers because as soon as an update reference, for example, we want to make sure that we're tracking that reference and updating it in our GC work as well. So with that, that's a very simplistic layout. And hopefully this gives you an idea of what would be needed with ZGC and what would be needed with the parallel collector. So let's go to a simpler collector, which is the Throughput Maximizer, which is the parallel collector in OpenJDK. So we want to be able to do two things with this, right? We want to make sure that we are not sharing resources with the application. So the application thread gets 100% of the CPU, for example. And then as soon as we're doing these collections, we're also compacting, because so if we keep on promoting these long-lived, it's great. But what about those medium-lived data or those transients that I was talking about? So they need to be reclaimed. That space needs to be reclaimed as well. but they could leave these kind of fragmentation holes in your old generation. And then there's no more space. And then, you either run out of space if you're not compacting, or you will have to, your out of memory error, errored out of it. So one of the easiest things to do is to fall back to a full collection. And that's what this throughput collector does. It's like, oh, I've run out of space here. So instead of calling for out of memory failure, let me go and employ the parallel collector, the old gen collector. And that's what you see, what you know as parallel old collector. And many times you will hear people talk about full GC. So that's the same collector. That's a parallel collector. People will also talk about a fail-safe collector. Again, that's the parallel old collector. And so that's very simple. So the direct relationship between throughput and your GC is that the GC will not take away resources from your application threads. Okay. So that means that we have to avoid any concurrent work. And that's what you see in your parallel collector. Okay. So let's get back to the design board. And this is where we were last, right? So we did the generational side of it. We did the parallel work, but with parallel collector, I mentioned one thing, that we don't want to do anything concurrently with the application, right? So if you wanted to change this particular design into a throughput maximizer, we just have to get rid of the concurrent work. So nothing will happen when the application is working. And there you have it. So to put numbers to this design, the parallel GC is only hopes to get less than 1% of an overhead. So when you plot this, your GC pause times, and you plot your application run times, your GC pause times should account to less than 1% of your application runtime. And that's the goal of the throughput maximizer. And I don't remember the exact command line option that you can use to adjust that, but do go ahead and read about that. It's very interesting. When I was learning about G1, I realized that G1 has the throughput goal of 10%. So G1 can, like in the worst case scenario, add up to 10% to your application throughput. So basically bring it down by 10%. So your application can only do 90% of its work because of the 10% GC overhead. But the throughput collector by design can only do 1% maximum, because then everything else, like all hell breaks loose if it goes more than 1%. So that's a simpler collector. You don't have to deal with any concurrent work, so no maintenance barriers. That's why it's kind of should get done faster, but doesn't scale well. The moment you increase your heap and you have this adaptive allocation rate and maybe high pressures, your throughput collector doesn't scale that well. So you have these very long pauses, the old gen pauses, right? Because it's doing a full compaction. So let's highlight the drawbacks that we have with respect to the full compaction. Like I said, it can get unpredictable and stalls that may lead you to even your 90th percentile may be really, really bad. So it's not just the tail, it's like the entire percentile graph that is like blown out of your SLA needs, right? And this usually happens because you have higher promotion rates. So your garbage collector. So if you think of it, if your heap size is not that big and you keep on promoting at a higher rate than the GC that can keep up, the young collections are just kind of premature promotions, etc. Then you keep on going into this long full gen cycles, right? Old gen cycles. And then you lose your scalability. So to be able to add scalability and predictability to your garbage collector, one thing we know what we have to go into that incremental. Remember, I was talking about how the full stop the world pause could be like divided, and we can do the GC work incrementally, right? So there's two concepts which help us do that incremental work. First is, don't think of the heap as a monolith, right? Don't think of the origin as a monolith. So the one way to not think of it as a monolith is to have regions in the heap. So I could say that my origin is made up of 100 regions, right? So now I have an accounting that, okay, 100 regions origin. What if I only collect 50 of them? So that my heap is, I'm not going to go out of memory or whatever, right? So that's the concept of regionalized heap. So we are trying to reduce the work, the amount of your unit of work, basically. So we can collect one region or up to the entire, all of those 100 regions. And so that adjusts our unit of work. And that helps us with partial compaction. So we're not going with this full compacting collector. We could do partial compaction. And with respect to doing work incrementally and still letting the application go ahead, we introduced the concept of concurrent phases. The first introduction that we had with respect to concurrent marking was in CMS. And then you also had concurrent marking in G1. Okay, so with these two concepts now, let's design a latency sensitive GC. So again, generational is still there. Everything about generational is still there. So if you remember that when we talked about parallel work last time, we talked about the stop the world threads, right? But now the same parallel work, we're going to do it in a partial manner, like incremental manner. So it's called partial compaction or incremental compaction. And in G1's case, it's called mixed collections. Okay. And we mentioned that to be able to do this kind of incremental work, we need the idea of regionalized heap because we want those regions to be the unit of work, right? That's how we determine what goes into a compaction. It's like, okay, 40 regions go into a compaction. So that way we can determine how to adjust the unit of work. And of course, we were talking about concurrent marking because we are employing concurrent threads. So we can identify that, hey, this particular phase of marking can happen along with your application threads. And because of that, we would have to have maintenance barriers, right? So this is what you would see in G1. So G1 is exactly this thing, but a lot of code, right? But this is the overview of G1. So what is the problem with G1? It's no longer long pauses. And I will show you, I have some numbers with JDK 17. It's about those tail latencies. And what that means is that up until like maybe 99th percentile, you're okay. But your 5 nines, like 99.999th percentile, people are observing really, really worse tail latencies. So remember, we were talking about predictable GC, right? And of course, scalable as well. So what we really need is a predictable, scalable, low latency garbage collector because we want to combat those tail latencies. So we talked about partial compaction, so let's keep that, okay? But what if we make it concurrent? So remember the compaction that was happening in a stop the world phase where we're talking about it in G1 GC's case, it's called the mixed collections. So there's a those happen in a stop the world pause. But instead of compacting during a stop the world pause, can we move the compaction phase to concurrent mode where basically your application threads are working and we're doing the compaction concurrently. So we're doing the actual movement of live objects in a concurrent fashion. Okay, that can be done, but what if we lose the race? So as you may know, concurrent collectors have to keep up with that, kind of with the mutated live object graph. They have to keep up with the allocation rate because we are also trying to move objects, right? So we want to keep up with the allocation pressure. So the way we do this is that we say, let's put time budgets. So when we're going from one phase to the other, sometimes we need stop the world pauses. So let's put time budgets so that we are more predictable and we kind of reach the next phase sooner and complete the work. So there are time budgets in Cgc, and I'll talk about where and what stop the world phases. But that helps with respect to maintaining that promise of sub-milliseconds pauses. Then, so what do we do if we exceed the time budget? We just cannot say, oh, I give up, right? So the next thing is that let the concurrent phases help out. So do some of the work to concurrently, and then go back to stop the world. So instead of an entire 10 milliseconds pause, you could literally do something like 2.5 milliseconds concurrent pause, 2.5 milliseconds concurrent pause, 2.5 millisecond concurrent pause, 2.5 concurrent. So you could basically divide that 10 milliseconds into this pause and concurrent work, right? And then what? We still have a lot of GC work to be done, right? So then you just rinse and repeat is what you do, right? So keep on doing the GC work in a stop the world concurrent, and then go through each phase in similar fashion until the entire work is done. Sometimes, even though you have the time budgets right, you are keeping track of the allocation pressure, but the GC is not able to keep up because maybe you haven't sized the heap correctly or whatever the reason be. At that time, what does the GC do? Instead of giving up, it cries for help. And basically it's asking the application threads to back off. And in some cases, it can ask them to help out. Hey, I have too much GC work to be done. So you've got to stop your allocations and help out with the GC work. So this whole thing is called self-healing nature. So Cgc does that as well. So basically it's asking the application threads to help out with the concurrent compaction, which means like, hey, help me move the live objects. Since you're trying to work with the same live object that I'm trying to move, maybe you can help move it. It's simple as that. So with these concepts, let's look at low latency sensitive garbage collector. So we have the generational, we have the regionalized heap, we have the parallel work, we have the same young old generations and maintenance barriers. Our parallel work is now going incremental, but concurrent marking, right? And compaction. So we're not only marking concurrently, which is similar to what G1 and CMS did, but we are also moving the entire stop the world compaction phase into concurrent phase, okay? And we are, if we need to, we can get help from the mutated threads. And now, because we're doing concurrent compaction, as well as we're doing some kind of self-healing work, we need more barriers. Anytime concurrent work is involved, you need barriers to maintain the accuracy of data, right? So Cgc right now, like today in JDK 17, doesn't have the generation. This is a work in progress. So I'm just gonna just mark it like as such. So if you go check a JDK 17 snapshot and you try to work with Cgc, you will not get the generation thing, work in progress. So let's dive into Cgc. If there are any questions right now with respect to the design phase, please go ahead and let me know.
There is a question actually, yeah. So this questions is, how are the sections to be removed from the regionalized heap actually removed? Is it done randomly or using the order of entry?
So usually it's based on occupancy and the least expensive region. So the more live objects you have in a region, the more expensive it is. So, and the reason is very simple. Your basic compaction is basically moving objects from one space to the other, right? So you're trying to make sure that all your live objects are accounted for, and usually at the bottom of the heap or whatever. So we're trying to compact it together to one space, right? And if I'm moving an expensive region from point A to point B, I'm using memcopy literally at the hardware level, right? I'm copying this data. So the more data that I'm moving, the more expensive. I'm waiting for it to happen, right? And if I'm doing it concurrently, it's expensive. If I'm doing it stop the world, it's still expensive, right? It just increases the pause time. So all GCs, concurrent or stop the world phases, they will want to go for the easiest, the lowest hanging fruit, which is regions with most garbage. So that's what the accounting is. When we do the concurrent marking phase, we figure out how many live objects are per region or how many incoming pointers are to the region, because that means the region is popular. So you don't try to move popular regions, because otherwise you'll be stuck updating those pointers. Remember those maintenance barriers? Those kind of pointers, you have to update them. So that's more concurrent work. Or if there's so many live objects, you move all these live objects, then you're spending time doing mem copies, and that's very expensive. So go for the lowest hanging fruit. Okay, so it's arranged in a ascending order, kind of, in a way. So lowest to the most expensive.
Right. Yeah, so it's able to prioritize essentially.
Yep.
Yeah, that's cool. I have a question actually. So on the last slide, I think it was, you mentioned that the generational GC isn't present in Cgc. I suppose from a practical perspective of using Cgc, what's the impact of that? Is that a problem for actually adopting it for like production workloads and things like that?
Yeah, it is a problem, especially if you're trying to get the throughput benefits that you are. So when I say that somebody is asking the application for help, right? So that means your application is not doing its work, right? It's helping the collector out, or it's slowing down its allocation rate, which means it's not able to do the amount of work that you wanted to get done, which means your throughput suffers. So anytime you're going into something that's trying to restrict its pause time goals, like, trying to say I'm going to be less than A, and basically it's thinking about itself. So you think of the garbage collector being selfish and trying to maintain low overhead in pauses, but at the same time, your application is suffering because it cannot do the work because the GC is being selfish. It's like, I'm not going to move unless you help out. So then the application is like, okay, I got to drop my work and I got to help you first. So that's exactly what Cgc does, because that's how it's designed. It's designed for that. So when it goes into generational, what basically you can think of the generation as like GC1 for young generation and GC2 for the old generation. So when you're doing work, so this one can do its work and it doesn't have to do the think about the other garbage collector that's on the old gen. The old gen will think about its own thing, and so it kind of gives you freedom. And old gen is like, why did you promote this? Kind of like they can nag each other too, so they can probably help each other out. But the point I'm trying to make is that your application threads are kind of more flexible with respect to the work they can do, and not be involved in this kind of problem, the GC problem, right?
Right.
So I think you will see that the GC will be very helpful. But let me show. I mean, the experiments that I've done is with the non-generational GC, and there is a very important use case. I think that people can start using that for that particular purpose.
Awesome, thank you.
So I wanted to define the design goals of Cgc. Cgc is meant to be adaptive, just like G1GC. The OpenJDK community is so used to getting hand-me-downs of command lines with respect to CMS and parallel GC with respect to survival ratios, young generation, the tenuring thresholds and all those things. And it was like, sometimes people didn't even understand. There was these performance gurus that did this work for that application for a particular underlying hardware, and then the hardware matured, the memory bandwidth got bigger, but these command line options just stayed. right? And the reason we had to do it because the GCs were not adaptive. The CMS was what it was, right? Throughput collector did try the adaptive size policy, but it backfired. So they were not designed to be adaptive, and we kind of resigned to the fate that it's never going to work. And so we did this kind of spoon feeding the garbage collector and telling it exactly what you want. But G1 and ZGC and Shenandoah and other collectors out there, they don't need this spoon feeding because they have this adaptive optimizations that they are aware of, that they can do, that they have the freedom to be adaptive. And in G1's case, if you try to kind of put this kind of ratios and thresholds and everything on G1, you're restricting it. So try not to do that. Let G1 do its job. If it's not doing it, then go fall back or go ask a performance guru like how to solve that. But so going back to ZGC, it's adaptive. It's got the near real time. So it's sub-milliseconds. That's the goal, right? And that's what you should see in JDK 17. It's scalable. So that's another advantage that all these kind of regionalized heap have, right? Because I said that now you're breaking the unit of work into these kind of regions. So you're no longer, hey, my heap is growing and now I have to, these kind of promotions, premature promotions are like triggering my old gen really at a faster pace. And I'm like, it's unpredictable. So just by adding this regionalized heap concept, you're making it more scalable and predictable. So that's those two words right there. And of course, it's a low latency collector. As I mentioned, it can guarantee sub-millisecond pause times. The pause times do not increase with application heap, live data set, or root set size. And it can span anywhere from 8 megabytes to 16 terabytes. So remember, I talked about the throughput goals. So throughput GC, the parallel GC, its throughput goal is 1%. G1 GCs is 10%. And ZGCs is 15%. Not that you should see those, because that's the worst case, right? But that's what, so to get back to your question, right? What do we see? Where is it right now? So we can see up to 15% drop in throughput with ZGC. But that's the goal. That was a design goal because single generational. So I'm going to quickly try to go over these things because there are many talks on these, but I think it's very important to highlight the core concepts so we can understand that it's a unique design and it's going to serve purpose more than it's like the ZGC because of the tagging bits. So the concept of colored pointers is also known as tagged bits, and what they do is basically you have like 4 different bits that you can talk to the garbage collector algorithm. So you could say that, am I in marking phase? That's like marked 0 and marked 1. Am I in remapped phase? And is this finalizable, the object finalizable? So it talks more to where in the GC process this object is lying, like where is it assigned to, so to speak, and what type of object it is. So very simple concept, but just by those tag bits, you can communicate so much more about the same object rather than making multiple copies of it. To get more details, please review Per Ledin's slide because he has a great talk. I think he probably has videos as well. But I haven't, I haven't watched the videos, but then this particular drawing is inspired by him. What do these bits do? They store metadata, and then that's exactly what a GC needs, right? For any kind of knowledge that you need about the object, right? You need to have certain metadata, and every GC handles it in a different way. And that's what it does with respect to, for ZGC, this is what it does, right? How how does this look at the OS level? Okay, so you could literally take these tag bits, and if your hardware allows it, then just talk to the hardware directly and let your OS just, pass through, right? Or in case of x86, what happens is that we can map it to 3 different spaces. It's called multi-mapping. So you could say, hey, marked phase, remapped phase, or the other marked phase, right? So we can have 3, normal, marked, remapped, all those things. So there will be 3 different spaces, and that's the concept of multi-map. And ARM64, although allows some tagging, like hardware tagging, but right now the only way it approaches this concept of colored pointers is by multi-mapping as well. So it's basically just this replica of what we do on x86-64. So multi-mapping, you have these in virtual spaces, and each tag bit represents which space you're going to address. Simple as that. So it's virtual. It's all virtual. So you're not making physical copies of these. So your data is not replicated. It's just a virtual copy, so that you just directly, it's like a virtual table. You're telling virtual table to look either A, B, or C, right? It's simple as that. So it's very fast. Almost no overhead. So with the concept of colored pointers, we spoke about the way we're going to reach these kind of the references, right? But what about the actual GC work that we're going to do? So let's look at that here in phases. We have our Java application threads, right? And because Cgc works with your application, like as your application is running, what I want to introduce is a concept of background threads, GC background threads. So at any given time, you will have something running in the background. This is what I mean by these background threads. And then when you want to start the GC phase, it is similar to any other collector, which is called pause mark start. Now, the name or the label, if you look at the GC log, it says pause mark start, but it's similar to initial mark. So when we talk about concurrent marking, every concurrent marking collector like that you know of in OpenJDK, that is CMS or G1, they call it initial mark. So pause mark start is nothing but initial mark. So that's where the marks object directly reachable by the roots, right? That's how we start our marking phase. Okay. And then we do something known as concurrent mark. Again, this is similar to what you do in G1 as well as in CMS, right? To do concurrent mark, where we do applications, live object graphs, you mark non-root objects, etc., etc. And then pause mark end. Again, new label, but it's the same thing that you would see in CMS as well as in G1 as well, and it's called remark. So when we talk about remark or mark end or I guess what was the other thing? I forget now. But so any of these concepts, basically, they're telling you that the concurrent marking phase is done. So there's a start flag, which is the initial mark, and there's an end flag, which is the remark. And between that, we're doing concurrent work. I will talk about how Cgc improves on these pauses, but the concept of these pauses is exactly the same as you have in CMS and G1 GC. Okay. So after we are done with the concurrent marking, in CMS you have there's something called sweeping, right? So you just pick out the dead objects. In G1 you have the process of mixed collections, which are stop the world pauses, and they will take out they move the regions, they'll compact the regions, right? So that the stop the world collection for mixed collection is now going to happen for Cgc as well. But remember, I said it's not stop the world anymore. it's concurrent. So basically, we're telling what Cgc is doing right now is doing all the preparation that you had to do before the mixed collection, where you do the liveness accounting and all the fun stuff. That is doing that's done in concurrent prepare for relocation. Relocation is same as reclamation, is the same as mixed, or so you could say like compaction or incremental compaction in our case, or mixed collections in G1 G6 case. But so basically you can replace this with concurrent prepare for mixed collection, right? So what I'm trying to say is that the concept of the GC work hasn't changed. It's just that GC work has moved to the concurrent phase, okay? And then this is the literal pause, which marks the start of relocation. So now the garbage collector is taking a quick pause and saying that this is where I'm going to, kind of any kind of metadata and methods or anything that it needs to unload. That's where it is going to do that. And then it sets the mask. Remember I'm talking about the colored pointer? And there's a remap phase in colored pointer. So that's where it'll set that kind of mask for the colored pointer. And then here is the actual copying that's happening. So you could have said concurrent relocation, concurrent compaction, concurrent collection. So it's the same thing, just new labels, but the work done is the exact same thing you can see in any other GC except for CMS, because like I said, CMS doesn't compact unless it's forced to, and it's a stop the world compaction. Okay, so that's the GC phases. And one thing that I wanted to quickly highlight, which I do with other collectors as well, every collector has its unique concurrent marking. If it's doing concurrent marking, it has a unique concurrent marking algorithm. And I wanted to quickly highlight how Cgc does its concurrent marking. Sorry. Okay. All right, so you have the heap, which is the contiguous heap right there. I'm not showing the regionalized heap here, but what I want to show here are how the work is done, how the GC work is done during concurrent marking. So your entire heap, and doesn't matter if it's gigabytes or terabytes, it will be divided based on the number of GC threads that are available to do the concurrent marking. So if you have n GC threads, your entire heap will be kind of like have these segments. It's called striping. And each of those stripes will be kind of assigned to these GC threads. So for example, you have GC thread 0, so you will have stripe 0, 1, and up to n, then again, 0, 1, n, 0, 1, n, and so on and so forth. So, and the GC threads know exactly to go for stripe 0. So this one, GC thread, once it gets done with 0, it'll go to this one, this 0, then it'll go to this 0, and so on and so forth. I'm sorry, I was not using laser pointer. So, so basically 0 will go here, and then next here, and then next here. 1 will go here, do the work here, and then do the work here, and so on. So every thread knows exactly what stripe to work on. So the concept of concurrent marking is that heap is divided into logical stripes. GC thread knows exactly what stripe they need to work on. And the goal is to minimize shared state. But that's the goal for every kind of work that you do in parallel fashion, right? Do your work, do work as much as possible in your own local state, and any kind of shared state, like, let's do it, put it to the last, because we know it will be kind of never going to be parallel because others have to stop working, and there's going to be only one winner that takes the shared state. Okay, and so how do we detect non-marked objects? So if the objects are not, the object pointers are not marked, how do we detect that? So we use load barriers. So that's the maintenance overhead that we were talking about. Anytime you have concurrent work, you have some overhead. In our case, we have something called load barriers. Okay. Cgc, and this is what I was talking about. So Cgc introduced the concept of concurrent reference processing because it wants to do it during concurrent marking. So reference processing historically has been done in the stop the world fashion. But because we want to remember, we're trying to shave away time from the stop the world phase. And this is where I was talking about, even though the phases are the same, we're improving the time we spend in the actual pause by taking away phases out of the stop the world and adding it to concurrent phase. So one of the important improvements that Cgc brought about is adding concurrent reference processing during concurrent marking. And then it also introduced thread local handshakes, which is now used in G1's case as well. And I'll talk about thread local handshakes very, very briefly, okay, after this slide. So I mentioned the barrier, and that's the overhead that we have with respect to concurrent marking. And I'm going to define what it means to have a loaded reference barrier, because that's a concept that was introduced again in Cgc and originally introduced in Azul's C4, right? So I have the original paper from C4 linked here so that you can go read more about the barrier. But primarily, a loaded reference barrier is simple. Is if you see a bad reference, that means a reference that has not yet been updated, then you make it into a good reference. That means you update that reference. It's simple as that. A reference that has not been updated will be updated, and that's the goal of the reference barrier. So anytime you find a reference that's not updated, you stop, you update it, and then you move ahead. So that's where the barrier comes in. So when I said the concept of self-healing or repairing, I mentioned that because it's basically work done to update the source memory location. So I find out that it's not updated, so then I go ahead and update it, and that's called self-healing nature. So whoever finds out, it's their responsibility to go and update that reference. And there are two sets of invariants that this particular, so all of the GC work and all of the accuracy of that is based on certain invariants that we have to follow. There's something called two-space invariance. That means that you will only have the right data in one of the spaces, either to or from. So the two-space means that it will be always in the two-space. So these kind of invariants kind of help GC maintain accuracy, maintains the correctness of the heap, right? So if you have a visible loaded reference value, right? The guarantee is that it will be safely marked through. So we will mark it, right? If it's not done, somebody is going to do it. Either the collector does it or the collector asks somebody's help to do it, but it will be done. That's a promise. And it will always point to the current location of the of a safe place where we can access the target object. So it's always going to be the right. So anytime you look at the loaded reference value, it would always point to the right place. So the guarantee is that you will never see a stale value, basically. And then anytime it is a bad reference, we'll make it as a good reference. So a good reference means pointing to the right place, and the value that you see is the right value. So pointing to the right place, pointing to the right value. That's basically the invariant with respect to loaded reference barrier. And as I promised, this is the paper, the original C4 paper that talks about loaded reference barrier. And so please go ahead and read that if you're interested in how this works. They explain it beautifully. Final concept is concurrent compaction. Basically, again, anytime you do concurrent work, we have maintenance barriers. In this particular case, in Cgc's case, it's called the load barrier, which detects pointers into the collection set. So anytime we want to move objects and the application thread is also working, guess what? We could at a point be trying to move it. So pointing it, we're maybe correcting it, right? And moving to the two space. But the application thread is like, oh, I need that object. What is its current location? What is it pointing to or whatever, right? So we check if it's in the collection set, which means we're going to move it, right? and we check if the application needs it. If the application needs it, then guess what? Let the application do the work, right? So that's called self-healing. So let the application do the work. And then one of the ways, and this is an optimization, how do we find out where should this object, this reference, the pointer move to, right? So there's a from space and there's a to space. We're moving it from the from space, but we're moving into the to space. How do we figure out where, so object pointer A is going to move to location B. How do we keep a track of what the mapping is, right? So that's basically done in an off-heap fashion. So it's really, really very easy. So you have this lookup table, so to speak, the forwarding table, and it tells you where to go. So it's like, oh, I'm looking for this object. Where do I go? Oh, go over here. So that's kind of that forwarding information is kept in an off-heap fashion. So that means that Cgc will need little more than just your heap. So the system that you're working on should have more memory, basically, because it has this off-heap forwarding table. But that also means that the release and reuse of virtual and physical memory is really fast. The moment you're done moving the live objects, all the addressable space is now available, right? Because it's off heap, so everything else is not tagged, not pointed to. So you're good to go. A quick overview of how Cgc became production ready. Started with thread local handshakes, right? Which is, I'll explain that briefly here. I talked about loaded barriers and colored pointers. I talked about concurrent reference processing, which was introduced in JDK 11. That's when Cgc was introduced to OpenJDK. Concurrent class unloading, again, moved the work of class unloading from the stop the world phase to concurrent phase. Uncommitting unused memory. Remember, I was talking about like if it's not in use, you can just like uncommit it and return it back to the OS. Windows and Mac OS support was added, as well as parallel pretouch was added in JDK 14. Compressed class pointers, because Cgc uses this tag bit, so it really cannot make use of compressed oops. But nonetheless, it can still do the class area, right? The metadata area, metaspace area. It can use compressed class pointers. So it started using that since JDK 15. Next is concurrent thread stack scanning, which is the last bit that let it achieve a sub-millisecond response time. That was in JDK 16. And 17 had some extended ARM64 support for Windows and Mac OS. So a quick overview of what I mean by thread local handshakes. Usually, when you have a save point that's requested, your application threads take their own sweet time to acknowledge that, because they're doing their work, right? So the last of the thread that comes to a halt here is the one that gates the entire time to save point. So the time to save point is basically the laziest of them all, right? And then once all the threads are so kind of like stopped, your GC threads can do its work, and then the GC completes its work, and then you go and resume your application thread. So this is your stop the world pause. It's not only the actual work done by the GC, but also the time to save point. And you will hear lots of people talk about time to save point. It's like, hey, the GC thread kind of finished its work, but for my application, because it was doing some JNI work or whatever, and yada, 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 it took a long time. So Cgc introduced the concept of thread local handshakes. So basically, what do you need? What information do you need from these threads? Why are we getting these threads to a halt, right? There is something that we need, the thread stack, for example. That's one of the easiest things that we can talk about. So why not go to every thread that has reached? So this thread, for example, was the first one to reach, to able to give its controls, right? So you say, hey, give me a thread information, stack information right now. And the thread complies. And then the thread can go and resume its work, and GC does its work here. Same goes with this thread next, and this one next, and eventually the last, the slowest of them all, right there. So these little handshakes are what is a concept of thread local handshakes. So when you When I talk about that initial mark, remember I was talking about the initial mark, stop the world fonts, it's basically comprised of these small handshakes. So that's why we can achieve that sub-millisecond pause times, because we're really not spending, it's not a global wait, but these small handshakes. And then the application thread resumes. So your stop the world is really like reduced from whatever this was to just these kind of small handshakes. And this concept, again, is not new. It's kind of new to OpenJDK, but also C4, Azul C4 also has a similar stop the world handshakes, but it's not global. Okay. Finally, to the best part, a few performance numbers and comparison with G1 GC. So one of the things I wanted to try, and this has been a problem with G1 as well. Like when you have fragmentation, which means that if you have humongous objects, so that's the easiest way to get a fragmented heap. Then G1 behaves a particular way because it's trying to keep up actually with the fragmentation and not give in to evacuation failures and full collections. Okay, so what I'm trying to do is like, so this is only with JDK 16 because I haven't repeated the experiment to 17. So I used a benchmark called Heap Fragger. This is by Gil Tenney of Azul. And as the name is, says it, right? It fragments the heap. It tries to fragment the heap. This particular system was big, is a big system, so I could do 200 gigs. And what I tried to do is like put a constant pressure on the heap. So basically 50% is live. So at any given time, 50% of the heap is occupied by live data, okay? The only two options that I want to give to this, except for the initial and max heap, is the large pages, because it kind of provides repeatability in experiments, especially when you're doing benchmarking. And always pre-touch, because it helps with the always pre-touch helps with like non-paging. So you won't find any surprises to, as you're manipulating the heap and you're like, oh, I cannot find anything. So I need to page in some the memory, right? So you want to do it upfront. So you pre-touch the entire area, till XMS, which is the initial heap, it pre-touches it upfront. So startup may be slow, but throughout your run, you're not disturbed by it. So I'm kind of like doing some benchmarking norms that people follow because we want repeatable, basically. Okay, so we want these numbers to be repeatable. Tested both ZGC and G1 GC. So if you check the benchmark out, you have allocation rates that you can specify, so I specified allocation rates. And as I mentioned, I want to make sure that I'm using large objects, so humongous objects. So the maximum can only, G1's heap size can be 32 megs, like regions, right? Heap regions. And so I've said more than that. So I've set it to 32, over 32. So it needs multiple regions basically for humongous objects. Okay, and as I mentioned, it's the benchmark is trying to do this kind of idea of fragmentation. So it does a bunch of allocations upfront, and you can think of it as if you're building your cache, like your in-memory database or whatever, and you're basically trying to populate all the stuff that you want to keep for long, and then you just have a bunch of transactions. So the things in blue is like you're trying to build your live data set, and then you have your steady allocation rate. As I mentioned, I set it to 1 gigs, 1 Gbps, so it's right there. That's one. If it's not that clearly visible, I'm just highlighting the area. So that's your steady allocation rate. I'm just trying to work with that, and quickly showing promotions. So the only thing that got promoted, and rightfully, is the initial, that you're building your data set, you're building your in-memory database so that you can save everything on the heap. So that's the only thing that got promoted. And that's exactly what we wanted, right? Because these are all transients. The other things that you see are just transients, that the transactions we're doing with the in-memory database. So what does how does ZGC behave? So there, with all these low latency GCs, we, as I said, GC thinks it's the boss, right? So it tells the application to back off or whatever, because it's trying to control its pause time, trying to not give in yet, right? In this worst case, the pause time was still less than 0.5 milliseconds. So we're still getting the pause time of 0.5 milliseconds. And because we asked the application to back off, we see stalls up until 350 milliseconds. So what I'm trying to say is that the GC maintained its low pause time promise, sub-millisecond pause time promise, right? And the way it did is like, hey, it said, hey, application, you have to lean in, which means that you may observe pauses, but I will never give you anything more than 1 millisecond. I am not going to go more than 1 millisecond. So the application leaned in, and at sometimes it was stalled because it was trying to help the garbage collector out because of the severe fragmentation that we were doing with respect to the heap. Okay. So how did G1 do? So here we can see the application with respect to G1 really couldn't keep up, and the application saw like 10 seconds of pause time, whereas ZGC, like I said, only saw like about 250 or something. So again, this in-memory database where you want to keep everything in your heap, and it's your LDS, right? And you have these transactions, you will see that people in the past used to try to get CMS to work with it, right? And sometimes even parallel GC, because you don't increase your heap. If you keep parallel GC in the 2 gigs range, you are happy. But this is not 2 gigs. We were talking about 200 gigs of data, right? So we're talking about how do we scale and what is the right GC. So this is single generation ZGC. It beats G1 GC hands down, right? Because G1 GC cannot keep up with the fragmentation pressure. And usually you will see that there are lots, the way you kind of bring this database into your heap is by large chunk allocations, right? And if you go anywhere over, even over 16 megs, then G1 GC will see fragmentation. I kind of handicapped it by going over 32 megs, but I'm just saying that you see the low latency GCs will come out as winners with respect to these kind of fragmented, heavier allocations. Okay. The next, I wanted to show similar pressure with respect to large objects, and now I'm going to increase the allocation rate even further. So you have fragmentation, and now we are seriously dealing in that higher allocation rate areas. So this is with JDK 17. And the benchmark is AWS's hyperallocation benchmark. This particular system had only about 100 gigs of memory, 120, I think. And what I did was like set the heap size to 80 gigs because I didn't want to, remember, I talked about the extra data structures that we have to maintain with respect to ZGC and even G1 for that matter. So wanted to give some room for that. And because I did a heap size of 80, my LDS, I kept it at 40 gigs. I kind of made sure that the benchmarking threads are all utilized. So basically whatever the CPU thread capacity was there, so I kept it to 80 because the CPU threads are at 80, and tested both the ZGC and G1. And I kind of had 4, 8, and 16 gigs of allocation rates. Now, if we're talking about normal allocations, these are already very high. But then in my case, I'm doing humongous allocations. So they're like these, you will see skyrocketing because humongous means that we're allocating chunks of object at this time, right? So I'm allocating again 32 megs or greater of humongous objects. So here's the graph with respect to ZGC. What you see on the left is the mark start. So basically initial mark, remember? So at initial mark, this is what ZGC saw based on the pressure that I was applying. As I said, I had 40 gigs of live data, right? So this is somewhere, this right here is 40 gigs, right? But because I mentioned about floating garbage and all those things, at any given time, because marking hasn't started, Cgc doesn't know how much of it is live. So it keeps a track of the live objects, which is awesome, but it doesn't know how much it is live. So it's always assumes it's like more than what is really live. The other thing, you see this higher line over here. So that's what is used. So basically, because I'm having transient, so you can think of like, this is pseudo live data set, and these are my transients, like the ones that will quickly die, short-lived objects, right? So, and this is the entire capacity, which is 80 gigs. So that's on the left. Now, Cgc did all its concurrent marking, it did concurrent relocation start, and then it finally moved all the objects in the concurrent fashion, and that's the end of it. So now the objects have moved. It has better idea of what was live because we're done with moving what we thought we should move, right? So look, it's closer. This particular line right here, it's the live that it has accounted for, and it's very close to 40, right? It's very close to 40. Yes, there is still some floating garbage, and it's always going to be there because it's the concurrent collector, but we're doing really well with Cgc. And then what do you see here? There's the used heap, right? So the used heap tells you that we did not collect the entire heap because we are trying to keep up with the allocation rate. So this is a true form of incremental compaction. So remember I said, if this was parallel GC, you would just see a single line here, right here, because my LDS is at 40 gigs, right? So you almost see a straight line here with parallel GC with respect to live, right? Although the collection you would see is a sawtooth. But what you see is that Cgc only wanted to reclaim whatever was LDS, whatever it thought was LDS, and any kind of noise over that is like, I don't care, I have enough headroom, so I don't have to collect that. That noise can stay. So this is a clear classic example of trying to do the balance between providing the right pause time goals and let some garbage lie. Like nobody cares because it's not going to be expensive. The more you keep it around, the more you can collect it later, because always go for the low-hanging fruit, right? So with that, I want to talk about the adaptiveness of Cgc. So in that particular example, what we saw was allocation rate, right? Right here. So everything in green. So we had so much allocation pressure that Cgc was dealing with just the allocation pressure, and that's all it was trying to do. So, but what are the other phases that Cgc has? Okay. So the first is the simplest one, which is like timer based. So anytime, so you have a timer of X, every time you have, so basically it's like you're going through exercise at the gym and you say, every 2 minutes, I'm going to move to the next one. And that's what you can think of it as GC cycles are basically exercises that GC does to keep the heap healthy, right? So every 2 minutes, for example, if that's what your timer is set to, will be like, I'm going to move to the next GC cycle because I need to keep up and keep my heap looking healthy. So that's just called, making sure that you don't have any surprises. And that's when you have no allocation pressure, nothing, everything, you give it enough heap and say, be happy, Cgc, and that's its default. The second one is warm up. Like if you start the heap, like I did with LDS of 50%, right? Basically, just based on that, Cgc is trying to get ready for it. It's like, oh, looks like there is some pressure, and there, there's my heap occupancy is like 50%. That's more than what I want it to be. So let me start a GC just to be proactive and see, if I can figure out my LDS. And as you can see, it figured it out pretty quickly, right? If we go back to the previous slide, right here, it figured out the live data set very quickly. But because it's trying to keep up. So, so in this particular case, this little sliver here you see, that's warm up, okay? Allocation rate, that's where we were. We were like there 99% of the time. And that's because we did give it high allocation. I mentioned that we gave it 16 gigs, but also most of that was humongous. So you're releasing hundreds of gigs of allocation, gigabytes per second of allocation, right? And the reason that Cgc goes to that phase very quickly is because it knows that not only is my LDS high, but also this allocation rate is really high because I'm getting these humongous objects coming in. So I need to make sure that I'm proactive. These are all called kind of keeping up with the application. I have another example, which I'll talk more about allocation stalls. And then there are other two ones too. Like if I did the higher utilization where I kind of make the LDS 80%, then I could go that. I haven't done that experiment, so I cannot talk to this yet. But there is a phase where Cgc will try to cover for higher utilization. And then there is something called proactive. It's like, I guess I had nothing to do for the last 5 minutes. And I think the occupancy is slowly rising. Let me just be proactive and do a collection so that I don't get pummeled with GC collections later on. So these are the phases of Cgc, and that's the adaptive nature of Cgc that I wanted to cover. And just wanted to show you the next slide. I wanted to show you how high my allocation rates were. You see how all these dots, those are basically all the collections that happened. So this basically mark start, mark end, and relocation started shown over here. So those Cgc was constantly busy, as you can tell, in that 10-minute cycle here. But even though it was constantly busy and was doing GC work back to back, pretty much it seems like, right? But the worst case pause time was only 0.026. This is 0.026 milliseconds. So it's truly a sub-millisecond collector, as they promised. How does this allocation rate affect the application? So as you can see, applications are seeing less than 8. So the worst case is 8 milliseconds. So even the application is less than 10 milliseconds, even though I kind of screwed the allocation rate so much, right? And kind of handicapped, tried to handicap the garbage collector. But it still did not let the application see or observe those kind of issues, right? So right here is somewhere up there is 10 milliseconds. So my SLA for the 99.999th percentile is 10 milliseconds. So the application did not even see anything more than for the 99.9, for the 5 nines, basically didn't see more than 8 or more than 7, I guess. So that's a very happy customer right there. Next, I wanted to compare quickly with G1. And this is basically showing all the stop the world pauses that G1 had. As you can see, it's like mostly in the concurrent start, basically initial mark, and it tries to reclaim everything. So it's doing its job. I mean, look, it's only 27.5 milliseconds is the worst case. And if you know the G1 default pause time goal is 200 milliseconds. So it's really tried to keep up and did a great job with respect to my allocation pressure. And if you see what did the application see? So the application sees a worst case of 31 milliseconds. Not bad at all. G1 is not a low latency collector. Still tried to deliver the application. It didn't try to stall the applications. As you can see, the worst case pause is 27. The worst case that the application sees is 31. So not bad at all. I'm pretty happy with the way it was designed. But then did we stress the collector or not yet? So we have this in-memory database and we put this LDS at 50%. But what if there were some medium-lived object now? So our heap of 100% in memory, whatever we want to keep in the LDS is 50%. Well, what if we had 25% of medium lived data? So these are like transactions that you're doing, but it's the transactions that you want to keep around because these transactions are doing, feeding other transactions. So kind of like persistence kind of you're maintaining the state of these transactions because they're feeding some other transactions. So your actual LDS, which is what your database is, that's where your transactions are happening against. Then you have some kind of persistent state that will live around for quite a while, not so much, okay? So let's go to that kind of scenario. Okay, this is just comparison between the G1 and ZGC just based on the SLA. So SLA is 10 milliseconds. G1 seriously blew the SLA, but I wasn't expecting it to be any bit closer to CGC. So like I mentioned, so we have 50% LDS, 25% MDS, which is medium data set size. And same system, same heap, same benchmark, everything is same except for the MDS, which is 20 gigs now. And everything is same, about pressure, object size, and everything. So if you just look to the left-hand side right here, you see how close we are to the 80. So ZGC sees pretty much the entire heap as live, right? And so basically about 75 gigs is live out of 80 gigs. And you can imagine it's basically doing back-to-back collections, right? So what happened at the end of this? So at the end of it, remember I had 40 gigs of LDS plus 20 gigs of MDS. So that's 60 gigs. So that's a 60 gig mark. Very close to that. So at every time CGC did reclaim things that it could, right? It could do that. And the noise above that is like, again, like I said, floating garbage or whatever. And still we are way below. So we did reclaim quite a lot, despite the allocation pressure, despite the medium data set side pressure, despite the humongous heap pressure, right? And how did our cost distribution look? So what you see now, we have allocation rate as well as allocation stalls. So this blue right here are the allocation stalls that the application was asked to help out. So basically, GC said, hey, you're allocating at a heavier rate than I can handle. So now you need to be blocked and you need to wait till I can finish my job, right? So that's exactly what here it says, allocation stall, muted or blocked due to lack of heap space. It's like, hey, you gotta wait. You cannot do anything right now because I need to figure out how I can keep up. So how does this look in your pause layout here? So, well, this is the worst case pause right there. It's highlighted right there. The worst case pause, even though it told the application to back off, ZGC still maintained less than 1 millisecond. It's actually the worst case pause that ZGC ever, that the application ever saw with respect to ZGC was 0.032 milliseconds. So you can literally see almost like straight lines. That's because the GC is working nonstop, right? It's trying to keep up. It did not give in. So the heap, it didn't run out of heap space. It did not give in with respect to its pause time goals. So it did great as far as I'm concerned. So remember, it did tell the application to back off, right? So how did the application react to that? So the way it decided to tell the application to back off was still very interesting. You see, it's kind of broken into chunks. So the application is still only seeing less than 10 milliseconds because all these kind of stalls right here are still broken down beautifully. So it's not giving you that 100 milliseconds stall. It's like back off for the entire time. It's telling it like incrementally to back off. It's like, hey, I cannot finish it, back off a bit. Cannot finish this, back off a bit. So it's like you see all these things is where it's asking the application to back off. And that's beautifully done. And while it's maintaining its sub 10 milliseconds pause time goal for the application. So it's a win-win with respect to that. So even with your in-memory database that's having some stateful transactions, it is coming out as a winner. And again, this is non-generational ZGC, right? How did G1 do? This is outside G1's comfort zone because of two reasons. We have humongous allocations, right? And already G1 is like basically trying to allocate everything in the old generation. And those things are hanging around. So you not only have humongous allocations, you are keeping them around as medium data set size, right? So what you see in blue is your full garbage collection process. So this line right here is where basically evacuation failures, because it ran out of space and it's crying for help. JIT is crying for help. It says, hey, your humongous allocations I cannot keep up with. And that's what gives start to evacuation failures, where it tries to reclaim space. And if it cannot do that, it does that in a full GC time span, like collections right here. So all these purplish blues are all full GCs. This kind of like the lower line is evacuation failures. But if you look at this, G1 GC, you know, if anybody remembers when we started back in JDK 7, update 20 or 40 or something, I would be happy to see this be like 15 seconds or so, you know, we're like, oh, well, not bad, 15 seconds. But you see here, it's in milliseconds. It's 75 milliseconds is the worst case that G1 saw. So G1 GC has seen so many improvements ever since that JDK 7, first time it was an experimental garbage collector, to now JDK 17. So in those 10 major releases, G1 has kind of kept up, and I'm very proud to see that it can give you 75 milliseconds in the worst case. How did the application react to G1's full GCs, right? Application didn't quite react favorably. It did see 220, maybe 230. So about 230 milliseconds is the worst case, and kind of like 175. So G1's GC's worst transformed into application's worst as well. So it kind of did cross its SLA goals, but nonetheless, again, G1 is not designed to handle that much of humongous object pressure, as well as you know, kind of keeping the GC to the top because it's trying to do the generational thing. So now I still want to experiment with CGC generation and see how it keeps up. So that would be another slide that I'll add once I get to that part of my learning. But yeah, here we are. And that was my last slide, I think. Yep. And here are some of the wiki pages. I haven't updated it to reflect the generational CGC, but all the logs that I used, or log formatters that I used, on all the tools that I used, and I think some links to the benchmark is on the test configuration pages. Yeah, and that's it.
Brilliant. Thank you, Monica.
Thank you.
Do you have time for a couple of questions?
Mm-hmm.
We have got some, yeah. Cool. So one question we've got is, how does ZGC deal with the situation when the application thread tries to modify or write to an object field during concurrent marking, i.e. when the application is trying to mutate the object graph?
Yeah, so that's when I was talking about the barriers, right? So if you go back to concurrent marking, slide back. That's funny. It's like one by one. I wish I could do something. If I remembered the slide number, I could have just done that, but I don't remember it. So we'll just wait. Okay, so here's concurrent compaction. We talked about the barriers, concurrent marking. So remember I talked about load barriers to detect. If the concurrent marking hasn't marked that object yet, and your application is trying to mutate or make changes to the live object graph while it hasn't reached that area yet. So there are barriers in place, and those are called load barriers. And that's what I was talking with respect to these kind of like loaded reference. So anytime it's not marked, it needs to be marked. And the way the CGC enforces it is by enforcing this barrier. So always update an unmarked to a mark is the goal.
Cool. I've got a question actually. So there's a bit you were talking about. Cgc uses off-heap memory for tracking. So I was wondering is there any kind of rule to kind of how much memory it will use based on heap size? I'm just thinking about like one of the challenges I've experienced is right sizing containers, for example, when you're kind of deploying Docker containers and things like that. And there's sometimes an ongoing battle, trying to get that right and, to and fro with kind of the size of the amount of resource that you're going to give to these different workloads. So yeah, just interested if there's any kind of rules there.
That's a good question. And I don't know yet because I haven't, one of the things that we want to do and probably eventually get to that is that make sure that we have tools that can look not only at the, I mean, we all got information on the heap size and we can see what's occupied on the heap. But sometimes, we want to do this. There's something called native memory tracking. I don't know if you've used that tool before. So I want to be more proactive. I've done this with G1 and I haven't done it with Cgc. So I'm going to write that down and then NMT with the slide deck. I will have to update you because I don't know it myself.
All right, yeah, no, that'd be brilliant. I'll look out for the update.
Cool.
That's great. We do have one more question that's come in. How does Cgc compare with other language GCs, e.g. .NET or Go, for example?
So very different. What are the assumptions or what are the necessities for those other collectors? It's very different than what we want from our low latency collector. Is compaction need with respect to other languages and how do they do it? So it's not just .NET, right? It's even like your client devices. Compaction means that you have sometimes even seconds worth of pauses that you don't want to see. Anything more than 30 milliseconds is probably too much already sometimes in some cases. So people do, many a times they will go to the incremental phases, but the way they handle this is very different and other collectors will handle it differently. I think I have seen OpenJDK garbage collectors to be one of the most sophisticated garbage collectors around. And I'm not just saying because of the newer low latency collector, I think even G1 in its innovation is more sophisticated than other garbage collectors. Now, I say this and everybody's going to come and tell me that, hey, .NET GC is the best one. And yes, it fits your purpose. Like if fits GC, fits the purpose of what it's designed for. We are targeting servers. We're targeting terabytes of memory. We're targeting low latency pauses. And we're meeting all those requirements. So just by design, I think it's a genius design. So sure, we can do this battle all day long, but I think for sure we are years ahead. OpenJDK is years ahead.
All right, cool. We have, I think it's probably the final question is, with the generational Cgc coming up, does it employ any card marking schemes to maintain the old to young pointers like other generational collectors, such as serial and parallel?
Yeah, it'll have to do all that, but I haven't looked at that yet, so I will not talk to it because I just don't. I want to learn. Like I said, if I have these assumptions made, what I've shown here are the design principles, right? So it will have to do it. Now, whether it does it via remembered sets like G1, GC, or like, how does it employ that? What are the queues? How does the log queuing happen? How does the buffering happen? All those things I still have to learn because I haven't looked at it. So it will come in due time. All that information will come in due time.
Awesome. Right, well, I think that is all our questions. So I think it's just, let's just say thank you very much, Monica, for joining us. That was amazing. Really interesting. We've recorded this evening, so we'll publish this on our YouTube channel shortly. But yeah, thanks very much.
Thank you for having me. I enjoyed doing all the experiments and keep reaching out and asking questions if you have any, and I will update as soon as I have more data and information as well.
Brilliant. Thanks again. Cool. And thank you everybody for joining, and see you all again soon.
Thank you.
Cheers.
Bye-bye.
Bye.
Yeah, bye.